The starry sky has always attracted people with its unearthly beauty. Trillions of other worlds lurk in its depths, which at this moment are quite inaccessible to us even. Our probes have visited all sorts of places around the solar system. They are not yet able to traverse the interstellar abyss to make a step to other stars. We need a new generation space engine, powerful and durable, capable of overcoming the sun's gravity and remaining fully operational for all the long years the interstellar journey will take. Until recently, such technologies appeared more like science fiction, but new discoveries bring them a little closer to reality. Let's try to figure out what a hypothetical hyperdrive of the future might be like. Modern spacecraft is hardly a secret. The distances in the universe are mind-boggling. Even with the best modern engines, a journey to the moon is going to take several weeks, and more than 6 months to reach Mars by the most optimal trajectory. If we think about the legendary voyages, after 45 years of traveling through space, they managed to leave only the inner part of the solar system. They are destined to spend several of the next millennia drifting through the scattered disk and the hypothetical old cloud. The fastest spacecraft of the moment is the Parker Solar Probe, whose speed in 2025 will reach a record-breaking 194 kilometers per second. However, this will happen only due to the sun's gravity, which will never allow it to leave the environs of our star. And so the probe is doomed to soon burn up in its photosphere. Apparently, chemical jet engines, which are currently so widespread, have exhausted their development potential and are hardly suitable for interstellar travel. Of course, there are various alternative concepts such as nuclear pulse propulsion or cellular sails, but implementation of either of these is hampered by a number of serious issues. It is highly likely that sooner or later most of these difficulties will be overcome. Another important task crucial for long-distance travel should be taken into account, namely the creation of a stable and powerful source of energy. All modern spacecraft are relatively small in size and are equipped with reliable but low-power power sources. For example, autonomous research probes are usually powered by isotope batteries, which inevitably degrade over time. If we revisit the legendary voyages, it turns out that almost all their systems have long since been de-energized, and the spacecraft themselves have been moving by inertia for many years. The ISS and other orbiting space stations combine solar panels and radioisotope thermal generators, but most of their power is consumed by life support systems, and the ion drives serve only to adjust the orbit in the case of an extended manned mission to a remote planet or star. However, a spacecraft would need much more power. Meanwhile, 99 of the way to another star inevitably passes through interstellar space devoid of obvious energy sources. Even radiation of the brightest stars is noticeably weaker here and dissipates in the vast expanses of space. Therefore, to energy source travel to other worlds, we need an autonomous, powerful, and preferably inexhaustible source of energy. To figure out a potential way of solving this problem, we have to take a closer look at the university's structure. It is that a number of amazing physical processes can be observed which might prove to contain a key to star secrets. To do this, we have to take a slight detour. In 2017, a collaborative effort of scientists from Princeton and Hong Kong yielded an incredible device that at first glance violates the fundamental laws of physics. A microscopic mechanism consisting of two silicon plates spaced 100 nanometers apart was able to generate a small amount of energy literally from nothing. It would seem that such a phenomenon should grossly violate the law of conservation of energy, one of the fundamental principles of the universe's makeup. However, in fact, it is not as simple as that. The Casimir effect, the amazing device, is based on the Casimir-Pelder effect discovered back in the middle of last century. Putting it simply, it boils down to this: if two thin plates are placed in a vacuum a very small distance apart, they will begin to be mutually attracted. The phenomenon is closely related to the Heisenberg's uncertainty principle, from which follows the existence of the so-called zero-point vacuum fluctuations. There are pairs of virtual particles that constantly appear at any point of the universe, by and large out of nowhere. However, their lifetime is only 10 to the power of minus 24 seconds, after which the particles disappear back into nothingness and the global balance is restored. At the same time, the virtual particles with any parameters are generated in open space. Only those that have strictly defined wavelengths can be generated between the plates. Consequently, more numerous external particles press on the plates. harder than internal ones. Just to illustrate, one can imagine that the space between the plates has a negative pressure. It's as if a little more substance were pumped out of the vacuum. The resulting mechanical tension can be transformed into an electric current, which is exactly where the Princeton and Hong Kong researchers did. And although the current was quite weak, it's a principle itself that matters, because this way our world receives energy virtually from nothing, even a low power source of. Inexhaustible energy is of enormous practical value, for example, as an autonomous power supply for microprocessors and other high-precision equipment. For example, the Voyagers equipped with such a hypothetical battery could still transmit data from their instruments to Earth. This opens up promising vistas for exploring deep space. Many interesting physical phenomena follow from the Casimir effect, one of which is the so-called Schoenhorst defect. According to calculations, the speed of light in the space between the plates should exceed the standard value of 300,000 kilometers per second because there are no collisions of photons with virtual particles. Although modern technology does not yet allow this experiment to be carried out, its mathematical justification leads to far-reaching conclusions. For example, the Alcubierre bubble, widely known project of the hypothetical superluminal engine known as Alcubierre's bubble, was proven to be potentially feasible by scientists from Baylor University, Gerald Cleaver and Richard Abusi. They combined the equations of quantum field theory and the general theory of relativity, producing complex but clear rationale for a bold concept. It is worth mentioning that according to quantum field theory, space has not 3 dimensions but many more, but this becomes noticeable only at the level of the microcosm. Applying the equations of this theory to calculate the Casimir effect, the researchers came to the conclusion that it is possible to control its properties with the help of a powerful energy impact. If we condense the space behind the Casimir effect drive hypothetical starship and make it more rarefied in front, then there appears an area similar to the Alcubierre bubble, which is capable of moving at superluminal speeds. The laws of relativity are not violated here because it is not the ship itself that is moving, but the space around it. On the other hand, from the very beginning, the main problem of creating such a bubble was considered to be the incredible amount of energy required. According to some calculations, an entire planet must be converted into radiation to form a sphere capable of accommodating a starship. If researchers manage to scale generators based on the Casimir effect to the required capacity, we will be able to obtain energy anywhere in the universe, literally from nothing. Of course, there are still many problems to address for a starship to be fully operational, because outer space is not the most friendly environment for humans. For example, it is permeated with deadly radiation, which not only destroys cells of living organisms, but also causes negative mutations in their offspring. Thick metal shields or magnetic fields with certain parameters may be used as protection against it, and both of these approaches have their advantages and disadvantages. Another potential threat could be accidental collisions with micrometeorites and cosmic dust at high velocities. Even a tiny grain of sand has incredible kinetic energy and can pierce through a metal plate. It goes without saying that on a long interstellar flight, repair options are extremely limited, and a hole in the hull may prove to be fatal. In addition, a long expedition without support from Earth requires creating a closed biosphere within the starship. Scientists from different countries are currently working on this. For example, various plants have been grown on board the ISS for quite a number of years, both for scientific purposes and for consumption. In addition to that, engineers are developing systems for recycling waste, including biological waste product. However, a fully fledged orbital ecosystem is still a long way off. Ending, of course, problems that space explorers may encounter are not limited to these. After all, we've only taken our first steps beyond our planet, and many nuances of the universe remain hidden from us. Obviously, the effects of such exotic fields on the human organism are still understudied, and in the future scientists are bound to encounter new challenges and solutions to which will lead to further discoveries. Who knows, maybe one of them will make us see the universe in a new light. Foreign. Thanks for watching. Subscribe for more videos like this.